Okay, so indeed, so it's great to be here and to introduce, to start the day. I'll therefore also give a bit of more context on mixed reality, and in particular computer vision for mixed reality, which is really what we're focused on. Very briefly, let's look inside, this device here, which is essentially, probably the most advanced mixed reality device that's out there. That's actually really available to customers, and that that people use every day in different applications. So that also really gives us the opportunity to learn a lot to push this forward. But let me show you a little bit why computer vision is so critical to provide this, to enable these mixed reality devices to operate and to provide these mixed reality experiences. So besides already important, just a camera to share what you are seeing with other people. This is of course a camera that when you use it, a privacy light goes on so that you can, that people know you are recording, but it's, this is so that someone else that's, for example, remote can see what you are seeing, right? And so can assist you in doing things. But then under the hood, there's many more sensors being used. In particular, here you see the device has essentially a stereo system here, plus a few, 2 additional peripheral cameras. This is really so that you can track the motion of the device very precisely and with very low latency. It's a combination of inertial measurement unit and this camera input. It very much works like our brain perceives motion in the world. We have 2 eyes, stereo in front of us. We actually have additional peripheral vision. I still see both of my hands here, very far from the center. I only see them monocularly. And then beyond that, we of course also have our inner ear system that essentially is an inertial system. And so very similar to how we perceive motion in the world, HoloLens is essentially doing the same. And why is this needed? Well, if I put on the device and I would simply display something here on each eye, and I move my head, what I display would move with my head essentially. So this is what we would call head locked. But if we want to actually place something in the world, we need to know very precisely how I'm moving, so that if I place a hologram here, when I move my head, the relative position between head and an object, virtual object, should change inversely with my motion. Okay, so we need to know very precisely that motion. In addition, we actually need to know it with very low latency. Actually, we can't compute fast enough, so the way, both in terms of computing the motion, but also in terms of rendering the graphics. And so HoloLens has additional, I'll talk about it in a second, hardware to try to hide that latency and bring the total latency, perceived latency, to below 10 milliseconds. Okay. Beyond that, other sensors, a depth camera, the one you see really in the middle there, it has essentially, it's a depth camera as you see there, so it for every pixel it measures the distance as well as a reflection. You actually see those next to the camera, which is in the middle there, you see next to it 2 illuminators. This actually also illustrates that everything in HoloLens is built to consume the least amount of power possible. So instead of having one kind of do everything kind of illuminator, there's actually 2. One that's focused on far away but more narrow and only a few times per second to measure the environment. And then one that's very wide field of view that's meant to track your hands anywhere in the field of view. But there, of course, the hands never go further than about 1 meter out. So essentially only needs to project much less energy but much more often. Okay, so reconstructing the environment. You can wonder why we need to reconstruct the environment. It's not virtual reality. It's mixed reality. It's augmented reality. So we see everything. But the key is that if you want to have in mixed reality, you want to have your virtual objects actually interact with the real world. So I want to be able to place holograms on top of real objects. So I need to know where the scene is. Also, I want, if I place a hologram here and you look from there, it should be occluded. So we need geometry for that. Now, as a byproduct, you can kind of integrate this and you could build like large-scale models, floor plans, etc. out of that data. At the same time, the hand tracking is done from this. So HoloLens has a built-in DNN inference engine that can find the hands, find different key points on the hands, and then from that actually do tracking of the hands. The small offset you see there is actually due to the fact that the camera is here, and the rendering is actually happening for one of the eyes, and that discrepancy is what you see. If you actually see this from inside the HoloLens, the hands and your hands and the virtual hands are perfectly aligned. Okay, so this allows natural interaction in the sense that you don't have to learn how to interact with those holograms. You can just essentially grab them or manipulate them as if they were real objects, and so it all is very intuitive. We can leverage what people know how to handle real objects, and we can leverage the same intuition to manipulate the holograms, thanks to this hand tracking. There's also eye tracking built in. These are these small little cubes that you can see in the HoloLens here. Those are cameras that look at your eyes, and then along the rim of the lenses, there's a few infrared LEDs that actually will reflect. So they're not visible to you, but they will reflect on your eyes, and they generate these glints. It allows you to find very precisely where the eye is located, and then by finding the iris, knows where you're looking. This is doing multiple things. So one thing is for interaction, can be built in interaction modality. Very simple example is you are reading a text, and as you're reading along, the system can know where you are in the reading and can automatically scroll the text along, as an example. But at least as important is also the biometric authentication. We can read your iris, and so we can essentially validate that it's who is using the device. And then in practice, actually the most important is being able to calibrate the display, because one of the key parameters is the interpupillary distance between your two eyes. Different people have their eyes at different distances. If you don't take that into account, if you just use a default, then it means that your stereo perception, which depends purely, the way you see the world depends on how far away your eyes are, and your brain is trained on this. And so if it's different, if you render it in a way that's different, you might see the world, all these holograms, as too big or too small in your stereo perception. But as you move around and you do what's called structure from motion, by moving around you also perceive depth, and then suddenly there would be an inconsistency between the depth that you perceive from moving around with your head and the depth you perceive directly through stereo. Okay? So if you get it wrong, you will not immediately notice something is wrong, but you will just feel that something's a little bit funny, and like after a while you might tire, kind of, this is kind of disturbing. Okay? So it's really important to get those things right, and just shows you a little bit all these layers under the hood that you have to get right to make things work. Then how can you do all of this real-time computer vision without a huge GPU somewhere to run your, your models on or so? It's really because there's built in, so Microsoft had to develop its an ASIC that essentially has a whole bunch of DSPs that run all of these real-time computer vision algorithms, plus a DNN inference core, which was specifically developed for the project, and also this depth-based late-stage reprojection, which essentially, think of it as an image-based warp that will take the image that was rendered by the GPU and then do a small correction on it based on the latest input from the IMU, which provides very low latency measurements, very easy to forward integrate and get a slightly better estimate. So the images are rendered based on a prediction from, or filter forward to predict where the image should be rendered, from what viewpoint the image should be rendered, so that it shows up in the right place, so that it looks like the hologram is perfectly static in the world. But then by the time it's rendered, you notice a small discrepancy. This hardware can essentially make a small correction to put it exactly in the right place. And as long as you weren't too much off, you won't see the difference. And so this really allows to hide latency, essentially, and bring it within 10 milliseconds, below 10 milliseconds, which makes it imperceptible. But all those things have to be right for the experience to be right? So this, and all of this needs to run all the time. So that's all in the front of the device. In the back of the device, you have a standard mobile processor, essentially, that runs all the applications and all the things. This also actually separates all of the raw sensor data, which could have a lot of privacy concerns and so on. All of that gets processed in these DSPs and so on in the front, and then only the output essentially things through APIs, standard APIs that tells you how you move, where you're looking, etc., but doesn't actually give access to the raw data. Is accessible to the applications in the back. Okay, here's some example of the applications, the most used applications on HoloLens. One is remote assistance. This is an example, actually a deployed example at Daimler, at Mercedes-Benz in the US. So essentially you get the person in the field. When they encounter a problem they're not familiar with, they can call up the expert at the central location for Mercedes and get essentially dedicated help of an expert that can see what the person is seeing in the field and can annotate the world. As you could see, they can place holograms, they can show up diagrams and so on to help, but they can also actually place instructions directly on top of the real world in front of them. So that's for special cases when you need an expert to help you. The complement of that is something where it's more canonical scenario, it's a maintenance task, it's an assembly task, something that people will have to repeat many, many, many times, and they have to learn how to do. Then they can get a mixed reality tutorial, as you see here. And you can see that this is much easier than to follow a YouTube tutorial or to read a manual of how to do something. Here, it's very intuitive, very simple, not to be misunderstood, step-by-step instructions, right? So that's this kind of thing, okay? Now, one thing, although these tutorials are great, one of the things is that they actually, HoloLens today, when it's doing this, is essentially kind of blind. It's essentially just telling you what to do step by step, but it doesn't actually follow along if you're doing things properly or not. So one of the things we're doing on the research side is to actually look at, can we make HoloLens smarter in a sense and make it understand what the user is doing? Within particular applications in these guide kind of scenarios, so what you see here is essentially a person doing a particular action. In this case, it was done from the RGB video. We recognize the pose of the hand, the object that's being manipulated, the task at hand, like opening, etc., and we can interpret all of that in 3D. And so this allows us to, this is kind of towards allowing us to understand what the user is doing. Here's some work. This was done actually also beyond the GRC collaboration. We also have collaborations with INRIA. And so this was actually Jana Hasson. She came for an internship, and we had then this paper in 2020 with her, where we looked in particular at using less training data to enable some of these scenarios. This is work, and you'll hear more about this from Tain Kwon, who's here in the room, who's a PhD student at ETH in my group, and also working with Microsoft in collaboration. This is a data set, H2O, so two hands manipulating an object. So the data set and then some strong benchmarks in here where we've carefully with multiple 3D cameras captured all of these interactions. And then here you kind of see the performance of the method we proposed and some of the previous methods interpreting this. You know, finding the pose of both hands and the objects that's being manipulated as first steps in that direction. Some more work that's coming up actually two papers coming up at CVPR that were done in the context of this work on essentially self-supervised learning for action recognition, with in particular as a pretext task for the self-supervision, essentially trying to align temporal sequences of video or of higher order sequences. So here's one example, and you see the paper at the bottom. So this was also in collaboration with Pascal Fouaille, one of his students that was interning with us. And so you see the reference, and then you see other actions that look quite different but have kind of the same gist, being essentially aligned you know, in a nonlinear way with the sequence in an unsupervised task as a pre-task, as a pre-training towards self-supervised action recognition. Okay, and then this, I won't go into any details here because you'll hear a lot more about this later. Tain will tell you about that later in the day. But here it's actually working not on the raw video material, but it's actually working on an intermediate representation, which is skeletal sequences here. Then here's an application in practice showing you, for example, how to replace a cartridge, where the system is actually shadow following along and seeing what the person is doing and interpreting that. There's a 5-step or 6-step procedure. And so as the person is progressing, it's essentially recognizing. And notice that this is an easy scenario because it's a more constrained scenario, right? These guided applications are in a sense kind of a narrow thing. It's not that the next step could be anything. No, there's a particular procedure you are following, and the task is essentially to recognize if the person is properly following that or deviating from the procedure. So in this case, person makes a mistake, goes straight for the cartridge without opening the cartridge, and so then it tells you that, that you should first do this other step. Okay? So another area where this is really important to understand and to assist people is in the medical space. There also you have first-line work, people that work with their hands in the field and that could really benefit from having access to a lot of information, in particular 3D information. And so here's an example of, in this case, this is a collaborator, Mazda Farshad, who's the head surgeon at the Belgrist University Hospital in Zurich. This is an example on it's switching back and forth between cadaver images and then an actual proper, this first surgery that was done of this particular type, supported by HoloLens. This was done 2 years ago. And so what you see here is they have to bend an iron bar that they will attach in the back to rigidly attach a few vertebrae in the spine. And they need to get at exactly the right shape. And of course, it's patient dependent. So they open the patient, they place screws, and then they need to place the bar in exactly the right shape. And it better fit, because if it doesn't fit, they have to go back and retwist it and try again. And then this takes more time, and this is more dangerous, et cetera, et cetera. And so here, they were able to immediately first go kind of get it bent the right way. They could verify it visually with the HoloLens, and then they could do. And the measurement was also done by HoloLens to get the right shape, et cetera. So where it really, using the HoloLens essentially really helps through its combination of 3D perception plus being able to display 3D information and so on. Okay, so in that context, there's work going on the research side of actually trying to capture all of this in 3D. We have a flagship project with InnoSwiss that's starting soon. This is separate. There's a project with Jonas Hein, which is in collaboration, co-supervised between me and then a professor at the hospital. And so we collect data set to essentially see how much we can track both the hands and the instruments in these type of settings. And here's the method we're using currently, which is an adaptation of what Jana was doing, Jana Hassan was doing in the more generic case. Let me skip for this. Also for researchers amongst you, if you want to use HoloLens as a research device, we have research mode, which allows you to, as I said earlier, normally you don't get access to all of the raw sensor data, but if you place a device in a specific research mode, which is a mode you can develop your own apps there and do tests. But if you do that, those apps you do, you can actually not put them in the store or upload them for privacy reasons. But you can, on your own HoloLens, you can essentially run all the experiments you want. You can get still access to all of the things that come by default on HoloLens, like head tracking, hand tracking, eye gaze tracking, and the RGB camera access. But in addition to that, you also get raw sensor access to the depth camera, both the wide field of view hand tracking camera as well as the 5 to 6 meters out depth camera for reconstructing the environment, the grayscale cameras that come from the head tracking, et cetera. So you can use all of those and get access to all of this and run your own algorithms on this, either on device or stream the data off device or record it to run your own algorithms. And at the bottom, you see an illustration of having integrated all the data, and then you see the head motion, which is this coordinate system that's flying around, as well as the cyan bar, and the dot is the eye gaze, and then you see the hands also being visualized. So all of this visualized in the same coordinate system, right? So you can imagine in egocentric computer vision that using this platform can be really quite useful. Then I want to show something that we've done in the lab. This was essentially one researcher in the lab that worked on this problem. So as I mentioned earlier, HoloLens normally operates in a mode where visual and inertial are perceiving the same motion. Actually, all of the system, if you have, augmented reality, AR core, AR kit, they all have a very strongly coupled inertial, visual inertial tracking system going on. But in practice, there are environments where this doesn't work. Which are those environments? Well, it's the environment where people get motion sick. Okay? So it's in a car, it's on a ship, it's in a plane. It's places where you're looking at you're inside a moving platform. You visually see mostly the moving platform, but you sense the external motion, the external accelerations. And so when you have that, you see HoloLens is essentially completely failing to track. These were some tests in the Redmond campus here in the car. And you see that it almost immediately loses track as when you're driving around. Not when you're standing still, it can hook in again, but then you start driving and you lose track again. Except if you drive straight at a constant speed, then of course you're fine also. Anyway, so we developed this moving platform mode, and now you see on the right here that they're actually, as you turn and move, it's actually not losing track anymore. So in this case, we're actually evaluating, we're allowing the two to diverge, and we also estimate essentially this divergence essentially has to do with how the platform moves through the environment. And so this way we can actually have now robust tracking also in these type of environments. Which, down the road is of course important in the scenarios here. This was Joshua who worked on this, doing this with his wife in the tram, testing out essentially the HoloLens tracking, seeing that just the system itself was stable and that the holograms would stay in place and not fly out the window essentially. And you can see now the tram is standing still. You can see it out the window there, but then it will soon start again to the next stop and so on, and everything keeps working just seamlessly. And here's another example. It turned out while we did it in collaboration with a car manufacturer, which was very interested in solving this, and of course down the road, when we'll get to these form factors and things that people wear all day, everywhere, they will of course want their glasses to also still work in their car and so on. But in the short term, much more important was in the marine space, on ships. Right? On the left, you see it doesn't work at all. It's continuously losing tracking and you have to restart and nothing works. And on the right, you can just have things work. There's a little bit more floating than in the standard case, but it still all works seamlessly, essentially. And so that's where, and this is now actually a shipping feature in HoloLens. So this is now in standard HoloLens. I explained you the scenario of remote assistance. Well, if you're on a ship at sea and a machine breaks down, it's very hard to get the expert to go visit you on the ship. If you're 1,000 kilometers at sea, it's essentially impossible. If you're in a storm and you really need to fix the machine, being able to call in the expert for remote assistance would be great. And you can do that through your satellite phone. But then, if the tracking fails, you can't actually kind of do it. So this is very important for Marines, all over the world for ship operators and so on to have this kind of capability. So, so this was a blocker that we were able to take away. Another thing, so there's a device on the one hand, but then there's really also the network. There's being able to benefit from, yes, I'm running out of time here. So, so essentially that's something that Julien will talk a lot more about. Also, if you have HoloLens, you can try it out in Mesh, but I'll leave that. So this communication aspect of being able to project your presence remotely and so on is something really important, and you'll see some of the things in that direction in Julien's talk. So I don't really have time to go here. I'll just show you some small things. The scenarios we want to enable is something like this. You walk around the factory, and you can access information. You can place information, and then someone else can come later and you can find information. Imagine here all the IoT information, all the digital information that relates to this factory is now not only visible in the control room or can be managed by AI for preemptive maintenance, but the person, the technicians out in the field walking around the factory can just see all that information and access all that information intuitively. For having that in the right context physically, you need to connect the physical space and the digital space. And that's essentially one of the key things the lab is focused on. So let me skip quickly for this. The idea is that the map that exists on a device that's needed for operating is going to the cloud. You can puzzle it back together in the cloud. Let me show you one example here of a really big space. There's a factory here somewhere in Switzerland. We just walked around with HoloLenses, 10 people walked around for a few hours, just in, amongst the whole space. And all of this got automatically puzzled back together into one big consistent map of the environment that you kind of see illustrated here. If you have that, you can also actually merge that together with other mapping devices. Let me show that here. So just to illustrate, so all the dots are actually HoloLens positions that were automatically registered and merged together with here a kind of laser-based capture system. And then you get this kind of digital twin, but connected to the real world. And if you walk in the real world or you walk in the digital twin, all of this can now be naturally connected. Okay. Same thing, bring robots in there. So I skipped through all of this, but essentially you can have people and robots just very naturally and seamlessly interact together in these spaces. Here's an example of 2 people walking around in our offices in Zurich, in the lab, and then also have a spot robot walk around in the same lab here. And you can see in the upper left, we have all of this being tracked essentially jointly in real time. Each device connects to the cloud and gets localized. For those of you in this space, there might be interest in essentially a benchmark that we're doing, and Andre is actually the right person to ask questions, and Mihai also in the back essentially we want to stimulate really people to not do single image kind of relocalization challenges, but really more representative augmented reality kind of continuous. You walk through an environment and you want to be accurately localized. Anyways, there was a preview at ICCV, but more is to come here and more is to be shown. I'll skip the privacy preserving, but Marcel will talk more about that. In particular, we've done a lot of work in that space. Marcel will talk to you about one of the things that's not on the slides here, on partial localization through that. Even the cloud doesn't know where you are. You will know from the cloud. The cloud will tell you where you are, but the cloud itself doesn't know where you are actually. But you'll hear more about that this afternoon. Anyways, lots of things in this space. Privacy is really important, so we're really looking at depending on the scenario, can we always provide, what are the privacy guarantees that we can provide and so on. To wrap it up here, mixed reality headsets can make a lot of difference. They can can help a user in ways well beyond what existing devices like your phone or your computer can do, because they have context. They can observe the user actions. They have context of the environment. They have at the same time as other digital devices have access to information from the digital information. And also it's natural and intuitive to get access to the information through natural user interfaces. Computer vision is a core technology there, and also HoloLens, great device for egocentric computing. I'll skip this, but essentially edge and cloud computing are really important here, the combination of both. And privacy is also really important here, and I'll leave it at that as I'm out of time. So thank you.
Okay, thanks for a great talk, Marc. Do we have any questions?
Could you tell us a little bit about the next generation of form factor that would make it easy to use everywhere? So just glasses like others are working on.
So I can't say much about that, but yes, you can assume that also at Microsoft we are of course very interested in HoloLens is the type of devices that we could build a few years ago now. HoloLens 1, HoloLens 2. We're going to build the next generations of that also. Those are devices that are really meant for people in the field having to do tasks, and where you can really, it's okay to have a device that's the form factor of a HoloLens. But obviously that's not a device that you would just walk around with in the street and so on. That's very clear to everyone. What's less clear is of course what, we all know what we want to build. It's this, okay? So a HoloLens in this form factor, great. Okay, we don't know how to build that yet, and nobody knows how to build that. It's essentially impossible with current physics or current, technology. So what's going to be interesting in the next few years is to see what trade-offs people are doing, right? There's a trade-off between cost, weight, battery life, like all different kind of parameters that are all fighting with each other. And so the question is, what experience will people favor? There's some companies that just have a glass like this with two cameras in, but doesn't do anything else, and so it's not even a smart glass. You don't even have any display integrated. Okay, to me that's pretty useless. But it's going to be interesting to see what different players, what route they will take to but it's clear that it's going to be many steps. What's really exciting to me of being at Microsoft is the fact that we have HoloLens, we have a device out there that people are using, day in, day out essentially, so we can learn from them, we can iterate. while all the others are still really kind of working in the lab and working in very limited kind of settings. So that's really exciting because we can essentially already learn and experience and build on top of that in a much richer way than if you're still just stuck in the lab essentially. So, but you can count on it that we also, just as all the other ones, we are certainly very interested in, as soon as we can build them and build a compelling proposition, we will do it. Yeah.
Hi, I'm Skanda. My background is mostly on audio processing, so my question will come from that side of things. For quite a few applications that was mostly sort of vision-based that you showed, for example, switching the cartridge in the printer, right? Mm-hmm. Most of these always have like an audio component to it. Like for example, if it is fit in properly, there's like a click, or in the car when you're doing some change, there's like a click, an audio feedback saying it's whether or not it's been sort of fixed properly. Mm-hmm. Is that something that you take into account, or you thinking about taking into account?
On both sides, yes. Audio is also really important. First, there's actually on the input side, there's a 5 microphone array built in. There's actually 3 environment microphones plus 2 near-mouth microphones. That allows you to essentially do speech recognition even in very loud environments, because you can really separate the speaker from the environment. So that's on the input side. Of course, there would be other applications possible with sound identification and directions and so on. So there's other things possible with this also. And then on the sound that's provided to the user, yes, it's feedback is very important. Audio feedback is very important. It's also something, the goal is really to have low cognitive load in providing information to the user. Certainly having some kind of ding or some, whatever signal that something is done and so on, that the system has understood you finished something, etc. Absolutely. That's not something, I'm very focused on, but in the general, it's really important. Also, what's really key is that HoloLens has spatial audio capabilities, of course, because you know exactly, as we know how you're moving and so on for the environment, you can actually localize sounds in the world, because, it is not using a very advanced kind of head transfer function or so, but it's using a default one. And the speakers are just here next to your ears. But yes, you can do spatialized audio, and so you can hear sound from there. In particular, that's actually used in HoloLens 1, there were some games that were very nice in the sense that they leveraged this. Although the field of view was limited, you would hear if something was happening outside the field of view, and it would draw your attention to it. Okay, so this is actually really used in HoloLens, and so the spatial audio, all these things are really important there. Yeah.
Thank you so much. Yeah.
Thank you very much for the presentation. I was curious about the algorithms behind, because, for example, this video where the person is pouring some milk, you have 3D object detection plus hand pose estimation at the same time. It's not the fastest one, but still it's pretty impressive. So you're using some very low-level C++ libraries for that, I guess?
Yeah, it's using essentially. I think it's probably using Python and with deep learning libraries and so on. Okay. For that particular work. But you'll hear more about some of this from Tane later, and you can chat with him to get more of the details.
But still, it's pretty impressive. Thank you.
Okay, I think we can have 2 more questions.
Perhaps to connect to the interesting question before about the audio system. So what it appears now is that basically the other sense that is missing in terms of rendering is the touch. Mm-hmm. Do you think this is really something to be looked for the future, or somehow human can handle with just the vision?
Well, so a few different things there. So I think, yes, the Holy Grail is certainly if you can add also touch. It's, of course, a very important modality, or sense. So that's in particular important. That's the most important, I would say, is in VR experiences where your world is fully virtual. I think for entertainment, for some applications, this would really make a huge difference if you can provide that. I think in many of those more professional applications, for example, you're actually in augmented reality, in mixed reality, mostly the things that you have to interact with, that you have to manipulate, are real objects. You just want to point to which objects you should pick up, like, in those scenarios, there the touch is actually mostly irrelevant because, the touch is not irrelevant, but the touch, you're actually touching real objects. And you're getting information about which one to touch, how to move it, this and that. So in that case, it actually is much less important. So it really depends on the scenario. So for some scenarios, it would be fantastic if you could add touch, add that sense of touch. And there are companies, working on that, and there are gloves and other things that can provide you some of this. But I don't know of any technology that is really very compelling yet. All of those require quite, heavy, complicated, expensive technologies. So I think it's still a long way out. That's probably one of the hardest ones to materialize. But in many of the, today useful commercial scenarios, it's actually mostly irrelevant. Actually, we don't need it because in mixed reality, right? Not in virtual reality. In mixed reality, we actually have the world to interact with in most cases.